Good afternoon, everyone. In his novel, The Lost Symbol, best-selling author Dan Brown takes us into an action-packed adventure, trying to unravel the mysteries of the Masonic Order. One such mystery is the lost symbol itself, which, according to the book, holds the key to the manufacturing of the Philosopher's Stone. The Philosopher's Stone, as you might know, is the alchemist's device capable of transforming lead into gold. An interesting idea put forward in this book, however, is that the Philosopher's Stone is actually a metaphor representing our ability to bring order out of chaos. Well, alchemy has, of course, long been replaced by science now, but I think this is an analogy that fits very well with the ongoing work of the metallurgists today. Certainly, the metals that we require today to build our infrastructure, to power our electronics, they started their life as chaotic mixtures of minerals on the ground. Of course, not through science, not through alchemy, but through science and technology. The metallurgists carefully extract, concentrate, and purify these metals, bringing them out from their original chaotic state. Now, metals can have a very high economic value, but they very rarely find application as pure metals themselves. So they rather are used as raw materials. And thus, I could say that there is an intrinsic contradiction between the metallurgist's work and the role that society plays in the use of such metals. Indeed, to use these metals, they have to be mixed and blended with all sorts of other materials. Thus, we are introducing chaos by design in order to produce useful products. Particularly in our technologically advanced societies, these blends and mixtures can become very complex. For example, if we think about the rechargeable batteries that are used to power our cell phones or the electric cars, these consist of cases of steel that protect layers of aluminum and copper that are by themselves used to sandwich particles of graphite and lithium cobalt oxides. So these are very complex. We are bringing chaos into this mixture. But of course, that's the only way we can make use of all of these raw materials. Society then further contributes to chaos when these products reach their end of life and we throw them away, and they become part of these huge piles of waste. This has been the status quo for centuries right now, but evidently this cannot continue. And I would say that we actually need to start changing the way we think of our relations with raw materials. And this is because the demand for raw materials is growing at a pace that is unprecedented in human history. Only to produce the batteries that should enable the targets on electrification of transportation and the support of clean technologies, it has been forecasted that by 2050, we will require 5 times more critical materials such as cobalt, lithium, and graphite to satisfy this demand. And this doesn't even account for instance, for copper required for additional infrastructure. So I think it's not responsible to think that we can supply this need by extracting activities alone. So as we have acknowledged this problem, it becomes clear why a model such as the circular economy has gained popularity in recent years. The circular economy tries to change the way in which we are using these materials, right? Instead of letting these products reach an end of life where materials will be lost forever, it has the specific goal of us harvesting these materials and reintroducing them back into the value chain, into useful life. This idea sounds very positive, of course. It has a very good goal in mind. But when I was first introduced to the circular economy concept several years back, my engineering mind asked a very fundamental question. Well, how do we measure it? How do we actually measure this circularity? Evidently, the access to parameters, to measurements, is fundamental for the engineering work. Because simply put, if you cannot measure, you cannot improve it. And engineering has a challenge because the type of parameters that we need to comply with some specific conditions. They need to be objective. This means that we cannot have just opinions. They need to be quantitative, and they need to be based on measurable physical or chemical properties. So what do we measure then if we are talking about the circular economy? Well, we decided to go back to the definition of the circular economy itself. Word of advice, there's hundreds of definitions published in the literature on the circular economy, but in general, the circular economy is defined as a regenerative system. It is an industrial ecosystem, and this means that we cannot use the same parameters that we have used so far when we evaluate transformation stages in isolation. It aims at reducing wastes, emissions, and leakages throughout this system. And that is actually what enables the circularity every time that we prevent materials from being lost. Because while the circular economy may look quite nicely in theory, there are losses of materials and energy at every single stage of the life cycle of a material or product. This is actually a way in which chaos is inevitably being introduced into our perfect circular system. And we do this by, well, we implement circularity then by slowing, closing, narrowing, by creating material and energy loops. So if it is chaos through the losses of materials and energy that we are trying to prevent with the circular economy, I ask myself, well, why not use chaos itself as a parameter? Fortunately, us engineers have a property that actually helps us measure chaos, and it is called entropy. Now, entropy is not such a simple concept to understand, so much so that when entropy was proposed as a term by Rudolf Clausius in the 19th century, one of his contemporaries said that he had succeeded in coining a word that meant the same thing to everybody. Nothing. It's not surprising to hear this because when you look at the textbook definition of entropy, you find out concepts of statistical distribution of microstates complying with macroscopic conditions of systems. But briefly speaking, for those of us unfamiliar with the term, entropy basically represents the irreversible losses of properties, for instance, energy and materials, as a result of any transformative processes. And so, using a very specific version of entropy called statistical entropy. A few years ago, we published the very first model of the circular economy based on engineering parameters. Under this model, the circular economy are a series of stages moving materials back and forth in their entropy levels. Every time we lose materials, entropy increases. And when we recover them, it decreases. This concept and this model was then applied for the design and optimization of recycling processes, serving the goals of the circular economy by design. But then again, bringing back these materials into levels of low material entropy does not come for free. It consumes resources, it consumes energy. It has inherent environmental impacts. So we decided to move forward and make more complex analysis of our parameters. And just last year, we published the first two-dimensional parameter of circularity as accounting simultaneously for the entropy of materials and energy. And we called it exentropy. Exentropy allows us to measure how much energy is irreversibly lost every time we recover materials. And what about the environmental impact? Are we actually improving the environment every time we try to recover those materials? Well, only last week, we published a methodology in which we were combining statistical entropy and life cycle assessment, allowing us to see which are the materials that are actually positively contributing to the environmental impact in terms of, for example, greenhouse gas emissions or resources consumption. Our purpose is to make these parameters available for all of you, for everyone interested on carrying out engineering work, so that they are considered every time you are trying to find out technological solutions supporting the circular economy. So as we can see, the circular economy is surrounded by many dimensions. We started by accounting for the material cycles with statistical entropy. Then we saw energy flows. Then we accounted for environmental footprint. And we could continue adding more dimensions. Lifetime of a product, or economic value, or functionality. And that would bring us to a multidimensional model. Now, for those of you who may not be familiar with this, the name of a multidimensional system, of a multidimensional circle, is a hypersphere. So what we are saying is that the circular economy requires a hyperspherical engineering for it to be properly designed. But wait a second. The hypersphere, is it not a geometrical shape with dimensions going beyond our physical realm, with the specific purpose of bringing order out of chaos? Have we actually found here the lost symbol? We have now come full circle as well in this presentation. But I want to finalize by sharing with you a quote that I think it may be food for thought. It's a quote from one of the greatest artists of the 20th century. David Bowie said, "Chaos is a very real part of our lives, and our refusal to accept chaos as being integral to our existence has been one of the greatest mistakes as civilization that we have made." And with this, I want to thank you all for your attention, and I want to thank that fantastic group of researchers sitting over there that have joined me in this adventure towards our own philosophy stone. Thank you very much.